Bismillahirrahmanirrahim and Assalamu alaikum dear student. Today is the 30th lecture of Discrete Structures CSC 102. In the previous lecture we were discussing graphs. In today's lecture we continue graphs, and in the previous lecture we had studied subgraphs and what is degree of verses in the graph and a total degree of graph. We have also discussed walks, trials, paths and circuits, simple circuits, and connectedness of graphs and what are the connected components of a graph. In the previous lecture we didn't have much time to discuss Euler circuits and how to find an Euler circuit. So in today's lecture first we shall discuss Euler circuits and how to find an Euler circuit in a graph. And further we shall discuss also Euler trials and how to find an Euler trial. We shall also discuss Hamiltonian circuits and a very famous problem which we can solve by using Hamiltonian circuits. And if we have time we shall also discuss matrices and graphs. So what is an Euler circuit? If we are given a graph G, let G be a graph, an Euler circuit for G is a circuit. Here Euler circuit is first a circuit, that is starting and ending point of circuit. Usually in the previous lecture we have discussed what is the definition of circuit. The starting and ending point of circuit is same, and edges cannot be repeated in a circuit, and or verses we can use them at least once in a circuit. So Euler circuit for G is a circuit that contains every vertex and every edge of G. Euler circuit is a circuit which contains every vertex and every edge of G. That is, an Euler circuit for G is a sequence of adjacent vertices and edges in G that has at least one edge. That is, in an Euler circuit we must have at least one edge. Starting and ending point is also same in the Euler circuit, and it uses every vertex of G at least once. That is, at least once means here that is vertices can be repeated in the Euler circuit, and uses every edge of G exactly once. What does it mean? It means that edges cannot be repeated and every edge must be used in the Euler circuit. But here the vertices, every vertex, of course every vertex must be used to construct an Euler circuit, but vertices may be repeated to construct the Euler circuit. So this is basically the formal definition of an Euler circuit. We shall discuss also with the help of examples how to construct, how to calculate an Euler circuit in a graph, in any graph G. Here is an important result which is related to the Euler circuits, which is a theorem. If a graph, any graph, has an Euler circuit, then every vertex of the graph G has positive even degree. Degree cannot, that is, degree can be 0. Therefore here in the theorem they have used the word positive. Positive means the degree must be greater than 0, and even degree, that is, every vertex in the graph must have even degree, 2, 4, 6, 8, 10, so like this. If the contrapositive of this theorem, that is, if a graph, if any vertex of a graph doesn't have even degree, then that graph doesn't have an Euler circuit. That is, we find Euler circuits within the graph. That is, if any vertex of a graph has odd degree, then we cannot find the Euler circuit in that particular graph. So this is basically a check in a graph whether there is an Euler circuit or not. Now we consider an example to check whether in the graph given here, whether there is an Euler circuit in this graph or not. So in this example, we have to show that the graph below doesn't have an Euler circuit, and we have to investigate by this theorem, or the contrapositive version of this theorem. First of all, we have to check whether every vertex of the given graph have even degree or not. So we check by starting the first vertex. This graph have 4 vertices, v1, v2, v3, v4. There is no other vertex here in this graph. So first v1 vertex has degree 1, 2, 3. So because there are three edges, 1, 2, 3. These 3 edges are incident on v1. Therefore we can say that degree of v1 is 3. So this is sufficient to say that if one vertex, at least one vertex, have odd degree, then this graph doesn't have an Euler circuit, using the theorem which we have discussed here, this theorem. So there is no need to check further verses, but even then we check what is the degree of v2. v2 has degree 1, 2, 3, 4. So there are 4 edges which are incident on v2. So degree of v2 is basically 4. And degree of v3, what is the degree of v3? v3, there are 3 edges which are incident on v3, therefore the degree of v3 is 3, and degree of v4 is 1, 2, 3, 4. So degree of v4 is 4. So according to theorem, as vertex 1 and vertex 3 have odd degrees, that is 3, therefore this graph doesn't have an Euler circuit, because it violates the statement of this theorem that if a graph has an Euler circuit, then every vertex of graph has positive even degree. So therefore we can say that this graph doesn't have an Euler circuit in this graph. Now we shall discuss the procedure how to construct an Euler circuit within the graph. Here is another important result theorem. The proof of these theorems you can see in the book of Discrete Mathematics written by Susanna in the chapter of graphs. This theorem states that if a graph G is connected and the degree of every vertex of G is positive even integer, then G has an Euler circuit. So this is another improved result which is better than this previous theorem. The next theorem has more information than this theorem. For example, here if we have a graph, for example this one, if we consider another example. Now consider this graph, this, here is a vertex, here is a vertex, we have for example and this one, for example, here is a vertex, here is a vertex. So this is a graph which has 4 vertices. For example, this is v1, this is v2, this is v3, this is v4. Now every vertex have degree 2, that is degree of v1. What is the degree of v1? 2. Degree of v2, what is the degree of v2? Is 2, because there are 2 edges which are incident on v2, v3 and v4, also on v1. Similarly, we can say that degree of v3 and degree of v4 is also 2. Now what? Every vertex have even degree. So according to this definition and according to this theorem, if a graph has an Euler circuit, then every vertex of the graph has a positive even degree. Now there is no problem in this graph, which is here. So there is no problem here in this graph, which is given here. In this graph, every vertex have even degree. So this graph must have an Euler circuit. So how to construct an Euler circuit? This is a question which we shall discuss later. But here you can see that this graph is not connected. We can draw this graph separately like this. Here we have v1, here we have v2, here we have v1, this is vertex v1, this is vertex v2, and the other part of the graph we can draw here. So here it is v3, here v2, here v4. So now this graph is not connected in actually this graph is not connected. So we cannot construct any circuit from v1, v2, v3, v4 which uses all the vertices at least once and all the edges exactly once. So we are unable, because v3 is not connected to v2, v3 is not connected to v4, or v1 is not connected to v2, v1 is not connected to v4. So we are unable to construct an Euler circuit. Even a simple circuit we cannot we cannot construct an Euler circuit here, because we cannot use all the vertices and all the edges. So according to the theorem and according to the definition, this graph, every vertex of this graph have even degree, but even then Euler circuit doesn't exist. So for an Euler circuit to exist in any graph, the graph must be connected. So according to this theorem, which we have this here, if a graph G is connected and the degree of every vertex of G is positive even integer, then G has an Euler circuit. So this is basically, this theorem gives us complete information when a graph G has an Euler circuit, that is when the graph is connected and every vertex of G have even positive degree. Now this is basically, this completes the information which we have to construct an Euler circuit, or whether there is an Euler circuit in a graph or not. Now the question is how to construct an Euler circuit in a graph. There are 3 major steps which we have to follow to construct an Euler circuit. The step 1 is pick any vertex v of G at which we have to start. So that is, in a graph, first you have to check 2 conditions: whether the graph is connected, and the second condition is whether all vertices have even positive degree or not. If these 2 conditions are satisfied in a graph, then there must be an Euler circuit in that graph. So now how to construct the graph, an Euler circuit in that graph? The first step is choose any vertex v of G, any vertex where you have to start to construct the Euler circuit. The second step is pick any sequence of adjacent vertices and edges starting and ending at that particular point which you have chosen to start constructing an Euler circuit. So pick any sequence of adjacent vertices and edges starting and ending at that particular point V, and never repeating an edge. Call the resulting circuit C. This is basically the circuit C which we have connected, which we have constructed. Now if C uses the circuit C which you have constructed, if C uses all the edges exactly once and all the vertices at least once, then this will be your Euler circuit. If not, then what? Check whether C contains every edge and vertex of G. If so, then C is an Euler circuit in step 3, and we are finished. If not, if this is not the case, then what we do, we follow the following steps. We perform the following steps, which are the sub parts of the step 3. Now step 3 part, or step 3A is, now remove all edges of C from G. That is, we remove, or you just imagine that we have removed all the edges of C from G, and also any vertices that become isolated when the edges of C are removed. And then we say the resulting graph which is left after removing all the edges in that circuit and isolated vertices from that graph. The rest of the graph which is left, we call this graph G dash. Here we have G dash, this is G dash basically. Now again, step 3B, pick any vertex W common to both C and G dash. That is the graph which is left, we see what is the common vertex, or what are the common vertices between C and G dash. Now we pick any vertex W, we say it, for example, W common to both C and G dash. And then step 3C, pick any sequence of adjacent vertices and edges of G dash starting and ending at W and never repeating an edge. Call the resulting circuit C dash. So we construct another circuit in G dash which starts and ends at the same point W which we have chosen, and we construct a circuit by using adjacent vertices and edges. We use edges exactly once, so that a new circuit is now being created or constructed. We call it C dash. Patch C and C dash. Now we combine together C and C dash to create a new circuit C double dash, so which is a larger circuit as follows. Start at V and follow C all the way to W, then follow C dash all the way back to W. After that, continue along the untraveled portion of C to return to V. We call it in step 3E C is equal to C double dash. We call the new whole circuit which contains C and C dash, we call it C. That is, C is equal to C double dash, and go back to step 3. If all the vertices and edges are not being utilized or not used in C or C double dash, then we go back to step 3. So this process continues until you get a circuit which contains all the vertices and all edges, such that all vertices comes at least once in that circuit and all edges comes exactly once in that circuit. So if this all the vertices and edges are not utilized in that circuit, we continue this process, and we know that the graph G is finite, that is, number of vertices and number of edges in G are finite. Then this process must terminate at some step or after some steps like this. And at the end, which circuit we obtain, that is basically the Euler circuit, which we have constructed in that graph G. Now we consider an example and we apply all these steps or this algorithm on this graph to obtain or to construct an Euler circuit. Now, first of all, the first thing you have to check about this graph before constructing an Euler circuit is that this graph must be connected. So what is the definition of connected? You know, we had discussed it in previous lecture. The graph must be connected, that is, any two vertices, between any two vertices in a graph there exists a walk. So if we look at the graph, we can observe that any two vertices, if we choose any two vertices, there is a walk between those two vertices, so this graph is connected. So the first condition this graph satisfies. Now the second condition, that every vertex in that graph must have positive even degree. Now we check all the vertices and their degrees. There are how many vertices in this graph? 1, 2, 3, 4, 5 and 9. So there are 4, 5, 6, 10 vertices in this graph. The degree of A is 2, degree of B is 2, degree of C is 2, degree of D is 4, degree of I and J is 2, degree of F and G is 2, degree of E and H is 4. So therefore every vertex of this graph has an even positive degree. So this graph satisfies the second condition also, which is given in the theorem, in the previous theorem which we have discussed. Now every vertex in this graph has even degree, therefore we can say that this graph is connected and every vertex has even degree. We can say that there must be an Euler circuit in this graph, and we apply the algorithm which we have discussed in the previous slide. Now we apply that algorithm to find the Euler circuit. So first of all, choose any vertex in this graph. For example, A is the first vertex, so we choose A to be the first vertex. Now what is the first step we have done already? Pick any vertex of G at which we have to start. So we have chosen A. Now second step, pick any sequence of adjacent vertices and edges starting and ending at A and never repeating an edge. Call the resulting circuit C. So in this graph we have chosen A. Now we construct a circuit that starts from A. So we construct a circuit like this. We say that we have A to B, B to C, C to D and D to A. So this is a circuit in this graph: A, B, C, D, A. So this is a circuit in this graph we have constructed. We call it circuit C. For example, here, so we have constructed here A1, we call it this H1, this H2, this H3, this H4, so that there is not any confusion. So we construct a circuit C which is A, B, C, D, A. So this is a circuit which starts from A and ends at A. So this is a circuit. Now the third step. What was the third step? Check whether C contains every edge and vertex of G. No, because still here we have used 4 vertices and 4 edges, and there are a lot of more vertices and edges which are not being used in this circuit C. So what we do next? If So C is an ILR circuit, so this is not the case, and we have finished. If not, perform the following steps. Now we perform the step 3a. Remove all edges of C from G, and also any vertex that become isolated when the edges of C are removed. Now what we do here, we remove all these edges. Suppose that this edge is not here, 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 and all the vertices which become isolated when we remove these edges. So A become isolated, B become isolated, C become isolated. So we remove all these vertices also. So what about D? D is not isolated here. D doesn't become isolated here, so therefore D remains here. So we get this graph. This graph is left here. We call this graph a graph G dash. Now this is basically the step 3a. Remove all edges from C of C from G, and also any vertices that become isolated when the edges of C are removed. Call the resulting subgraph G dash. We call it G dash. Now what is the step 3b? Pick any vertex W common to both C and G dash. Now W is any vertex of G dash which is common to both C and D. Now what are the common vertices of C and G dash? Because this is basically C and this is G dash. What are the common vertices? D is here, which is common vertex in C and G dash. So we pick up D here in the step 3b. Now what is step 3c? Pick any sequence of adjacent vertices and edges of G dash. That is, we again construct a circuit starting from D and ending at D, starting and ending at D, and never repeating an edge. Call the resulting circuit C dash. So now here we construct another circuit which starts from D, goes to E, then G, H, J, I and D. So this is basically another circuit. We call it C dash, which is D, E, G, H, J, I, D. So now patch up C dash into C. Here we have C dash. What is C dash? This is D, E, G, H, J, I, D. Now what was C? C was basically A, B, C, D, A. Now how to patch up C dash in C? Now here we have D, and insert here D to D instead of here in D. So this is how we patch up C dash into C. We write here again A, B, C, D. Now here with D we have E, G, H, J, I, D. Now suppose this is D to D, and here we have after D A, so we write here A. Now this is how we patch up C dash into C. Now we have another circuit, this one, which starts from A, ends at A and goes like this: A to B, B to C, C to D, D to E, E to G, G to H, H to J, J to I, and I to D. So this is, we call this new circuit which we obtain by inserting C dash into C. We call it C double dash. This C double dash we call it, and this is this new circuit which we have constructed. Now again call C double dash to C. We call it the circuit C, as was here in steps. Here we have patch C dash into C, or patch C and C dash together to create a new circuit call it C double dash as follows. Start at V and follows the procedure which I have shown you. Now let C is equal to C double dash. Now and then go back to step 3. What is the step 3? Check whether C contains every edge and vertex of G. If so, C is an ideal circuit, and we are finished. If no, perform again the step 3 A, B, C and D, E. So now here we check now whether this circuit C double dash or C, which we call it C, this contains every vertex and every edge of the graph. No, because there is a vertex F which is left, which is not here in this circuit. We can see immediately F is not present in this circuit. So still we are not finished. Now what we do, we repeat all the steps in step 3. We remove all the edges. We remove this one, remove this one, 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 this one. So if we remove all these edges, what we are left? We left only E, F, H and this E, F, H. So we are left this, we call this graph a G dash, or you can say G double dash, just to avoid the confusion between G dash. Now we repeat the step 3A, which is remove all edges from C of C from G, and also any vertices that become isolated when the edges of C are removed, call the resulting subgraph G dash or G double dash. Then we pick up any vertex common to both C and G dash. So here we had this graph G dash. Now so now what are the common vertices in C and G dash? These E and H are common vertices because H is also in circuit C, and E is also in circuit. Now there are two vertices which are common in the circuit C and circuit and the graph G dash. Sorry. Now we can pick up any vertex, E or H. Any vertex, it's up to you, but you choose. I choose E, and I construct a circuit from E to, you can say E to H, H to F, and F to E. So this is a circuit basically E, H, F, E. So this is another circuit, you can say it C dash. As we are repeating the step 3, therefore don't confuse with the notations which we have already been used, C and C double dash. Now we are again at the start of step 3, because this whole circuit which we have said it C double dash, we again call it C. So now we are at C, and the next circuit which we construct, we call it C dash. Now again what we do, we patch up C and C dash. This is basically C dash, E, F, and this here he has created circuit like this, E, F, H, E. This is also valid, and you can construct a circuit like this, or what I have constructed here, I have constructed E, H, F, E. So both of these are correct. You can use either of these two. Now patch C dash into C's. What was C? C was basically here given A, B, C, D. Here we had E. Now just insert E here in this, and we have inserted here E, F, H, E here. E to E. This is inserted here. You can insert this one also here. So now check whether C double dash, we call it C, now check whether C contains or used all the verses A, B, C, D, E, F, H, E, G, H, J, I, D, A. So it uses all the verses given in the graph. And here E is a repeating vertex, E is a repeating vertex, and first and last is also repeating. Now check whether every edge is being utilized, is used in this circuit. 1, 2, 3, 4, because AB, in AB there is edge 1, in BC there is edge 2. You can check 1, 2, 3, 4, 5, 6, 7, we go here 8, 9, 10, 11, 12, 13. So every edge has been utilized here in this circuit, every vertex has been utilized. So therefore, and also one more thing, every edge has been utilized exactly once. So edge is not repeating here in this circuit, therefore this is an Euler circuit which we have constructed in the graph, in the graph G. So since C includes every edge of the graph exactly once, C is an Euler circuit for the graph. So this is how we can construct an Euler circuit from the graph, from any graph G which is given. So now what is an Euler trial? Let G be a graph and let V and W be two distinct vertices of G. Distinct means they are different, they cannot be same. Let G be any graph, given graph, and let V and W be two distinct vertices of G. An Euler trial from V to W is a sequence of adjacent edges and vertices that starts at V, ends at W, passes through every vertex of G at least once, and traverses every edge of G exactly once. This is a bit of same concept here. In Euler circuit, the starting and ending point is same, but here in Euler trials, the starting and ending point must be different. Because V and W be two distinct vertices of G. So an Euler trial from V to W is a sequence of adjacent edges and vertices that starts at V and goes at W, ends at W, and passes through every vertex of G at least once. That is, vertices may be repeated, and traverses and passes through the edges exactly once. So there is an important result which help us to construct Euler trials for given graphs. It's a corollary. Let G be a graph and let V and W be two distinct vertices of G. There is an Euler path or Euler trial, we can say it Euler path also, from V to W if and only if G is connected. G must be connected. V and W have odd degree and all other vertices of G have positive even degree. So to find an Euler path in a graph from one vertex to some other vertex, not same vertex, the starting and ending point must be different. And here there is a change, there is a difference in the definition of Euler path from the Euler circuit. That is, the starting and ending point must have odd degree. That is, it could have 1, 3, 5, 7, anything. So the starting and ending point must have odd degree, the graph must be connected, and all other vertices except starting and ending point must have even degree, positive even degree. That is, it could be 2, 4, 6, 8, anything. So now we consider an example how to construct an Euler trial. This is basically we follow the same procedure as we have used to construct the Euler circuit, but here the starting and ending point is different. Here is an example of a floor plan shown below is for a house that is open for public viewing. For example, a museum. In a museum there are different rooms, there are different sections, and starting and ending point may be different just for avoid the overload in the ways, so that the people can move easily. Is it possible to find a path that starts in room A, ends in room B, and passes through every interior doorway of the house exactly once? If so, find such a path, such a trial. For example, in a museum there are rooms A, B, C, D, E, F, G, H, I, J, and a visitor came to the museum to visit it, and there are different rooms, different sections in the museum, and the visitor, obviously, he tried to see every room and the antiques in every room, and he, due to the shortage of time, that is every person in this time, he doesn't have much time to spend. So he tries to visit the museum, and he tried to visit each room exactly once, for example. So now we have to find an Euler path, so that path he follows, and he can see all the rooms, all the antiques in a given room. So here, is it possible to find a path that starts in room A? So the starting point is room A and the ending point is room B. So he enters here from this room, he goes out from this room, and he travels in all the museum, for example, or it could be a park. He travels in he visits every room and then go out. So we have to find an Euler path in this. First of all, we simplify this floor plan, and we draw, you can say, a graph which represents the ways of this whole plan. So this is basically the graph which represents the all possible entries and ways of the floor plan of that museum or a park. Here the person can go from A to G, that is from A to G, because there is a door here and there is a door here. So he can go from G to H, he can go from H to I because there is a door here, he can go from H to E, he can go from I to E, and he can go from E to K, there is a door here, he can go from K to J, from J to D, from D to C, and B to C, and from B he can go out. This is out, this is in. Another here, from H he can go to F because there is a door here, from F he can go to E. So if we sum up all these ways, we obtain this graph. Here the floor plan of the house be represented by the graph given by. Now we have to construct an Euler path, so that every vertex has been used and every at least once, and every edge has been used exactly once. Starting and ending point must have odd degree, the graph must be connected. All these conditions, first we check. The degree of A is 1 because only one edge is incident on A, degree of A is 1, and degree of B, the ending point, is also 1, because there is only one edge which is incident on B. So the starting and ending point have odd degree, so it satisfies the first condition. Graph is connected, yes, this graph is connected, so second condition is satisfied. All other vertices must have even degree. G has 2 degree because there are 2 edges which are incident on G. G has degree 2, H has degree 1, 2, 3, 4, I have degree 1, 2, K have degree 1, 2, E have degree 1, 2, 3, 4, J have degree 1, 2, D have degree 1, 2, C has degree 1, 2. So all other vertices have even degree, even positive degree, so all the conditions here are satisfied. Therefore we can say that there must be an Euler path in this floor plan, in this graph. Now we have to see it by using the same procedure or somewhat different. You can construct an Euler path here from A to G, G to H, you can go H to F, you can go H to I. There is another path, so this H to I to E, E to again H, H to F, H to E, E to K, K to J, J to D, D to C, and C to B. So here he comes in, and from here he goes out. So this is basically here, if we write it, this path, this is A, G, H, I, E, H, F, E, K, J, D, C, B. So starting point A, ending point B. So it uses every edge exactly once, yes, and every vertex at least once, yes. H is repeating here, so it satisfies all the properties of Euler path. So this is an Euler path. You can construct some different Euler path. For example, this is again another Euler path from A to B, but it uses some different path, but it is also still an Euler path also. So you can change the path, but it should satisfy all the conditions that first and last vertex must have odd degree, all other vertices must have even degree, every vertex must be used at least once, every edge must be used exactly once. So you can construct many other different Euler paths here in this graph, which are also the correct paths. So this is how we can construct an Euler path and Euler circuits. Now we move to the Hamiltonian circuits. This is basically somewhat similar to Euler circuit, but some conditions are different here in Hamiltonian circuits. We shall discuss also some application of Hamiltonian circuit also. Given any graph G, a Hamiltonian circuit for G is a simple circuit. Euler circuit was a circuit. This Hamiltonian circuit is a simple circuit. In a simple circuit, you cannot basically repeat edge also here. For G is a simple circuit that includes every vertex of G that is a Hamiltonian circuit for G is a sequence of adjacent vertices and distinct edges in which every vertex of G appears exactly once. Now every vertex of G appears exactly once. Now here vertex cannot be repeated here, but whereas in Euler circuits we were allowed to repeat the vertices. In Hamiltonian circuits the vertices are not allowed to be repeated, except for the first and last. That is, first and last are allowed to be repeated, which are same. Here it is basically a simple circuit, so edges cannot be repeated. But here they Hamiltonian, he doesn't give any condition, he doesn't impose any condition on edges. Edges will not be repeated, but edges, it is not necessary that this circuit includes all the edges. So this is condition. Basically there may be less number of edges than the graph may be used in the Hamiltonian circuits. So what is basically the difference between Hamiltonian and Euler circuits? There are two differences. In Euler circuit the vertices may be repeated. Here in Hamiltonian circuit vertices cannot be repeated and all vertices must be utilized. Second is, in Euler circuit all edges must be utilized exactly once. Here there is no condition on edges, so here you can see that note that although an Euler circuit for a graph G must include every vertex of G, it may visit some vertices more than once and hence may not be Hamiltonian circuit. So it's not necessary that every Euler circuit is Hamiltonian and every Hamiltonian is circuit is Euler circuit. So on the other hand, a Hamiltonian circuit for G doesn't need to include all the edges of G and hence may not be an Euler circuit. So either of two may not be same. So now there is an important result in which the conditions will help us to find an Hamiltonian circuit in the graphs. If we are given a graph G and it has a Hamiltonian circuit, then G has a subgraph H with the following properties. Now the Hamiltonian circuit basically is a subgraph H which has these properties. H contains every vertex of G, that is, every vertex will be also in H. H is connected, H must be connected. H has the same number of edges as vertices. Here it's an important condition, we'll discuss it in the example. The fourth condition is every vertex of H has degree 2. This is another important condition we shall discuss in constructing Hamiltonian circuits. So for example, here we have to show that a given graph G doesn't have a Hamiltonian circuit. Prove that the graph G shown below doesn't have a Hamiltonian circuit. The graph is given, there are basically A, B, C, D, E. There are 5 vertices and 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There are 6 edges. Now according to this result theorem, the third condition, H has the same number of edges as vertices. Here H has 5 vertices, 6 edges, so it doesn't satisfy the third condition of that result, the theorem. So there doesn't exist an Hamiltonian circuit in this graph. We can say that. The proof of this theorem you can see in the book of Discrete Mathematics written by Susanna. This violates this third condition here. H has the same number of edges as vertices. So there are 5 vertices and 6 edges. So we cannot construct a Hamiltonian circuit in this graph. We check other conditions as well. Here H contains every vertex of G. H is connected. Every vertex of H has degree 2. This is the fourth condition here. Here we have to construct a subgraph, which is basically Hamiltonian circuit, and which must be connected also. We suppose that there is some subgraph H which is Hamiltonian circuit of in this graph. Now every vertex must have degree 2 in that subgraph. Here A have degree 2, E have degree 2, C have degree 2, D have degree 2, but B have degree of B is 4. So we have to remove at least two edges, either this one or this one, or this one and this one, or this one, this one, this one, this one. We have to remove two edges from this vertex B to reduce its degree to 2, because in the result every vertex in H must have degree 2. If we remove this edge and this edge, the graph will not be connected, the subgraph, because, and also the degree of A becomes 1, degree of E becomes also 1. So we cannot remove this edge or this edge. If we remove this edge, degree of C becomes 1. If we remove this edge, degree of D becomes 1. So we cannot remove either of these 4 edges from this graph, otherwise this graph will be disconnected graph if we remove these two or these two. So we can say that there doesn't exist any subgraph of this graph in which every vertex has degree 2. So we can also say that this graph doesn't have any Hamiltonian circuit. So this is basically the detail we have discussed already. You can see it. So hence no such subgraph H exists, and so G doesn't have a Hamiltonian circuit. Next, a very famous example of a traveling salesman. Here's a problem. Imagine that there is a salesman who have to deliver his product into 4 different cities by using some roads and paths. So imagine that the drawing below is a map showing 4 cities and the distances in kilometers between them. So here this is basically from A to B there is a 30 kilometer distance, from B to C 30, from C to D 25 kilometer, from B to D or D to B there's 25 kilometer, and these are all basically given in kilometers. Suppose that a salesman must travel to each city exactly once, starting and ending in city A. Which route from city to city will minimize the total distance that must be traveled? So एक सेल्स पर्सन है जिसने मतलब किसी कंपनी की प्रोडक्ट्स जो है 4 डिफरेंट सिटीज़ में डिलीवर करनी है, तो वो क्या रास्ता इख्तियार करे कि उसको मिनिमम डिस्टेंस ट्रैवल करना पड़े। एक तो मिनिमम डिस्टेंस क्यों भाई, क्योंकि उसने पैसे बचाने हैं अपने। अगर वो मोटरसाइकिल पे जाता है तो उसने पेट्रोल बचाना है, अगर वो गाड़ी पे जाता है तो डेफिनेटली टाइम और पेट्रोल और या गैस उसने बचानी है। तो डेफिनेटली he will choose that route to deliver that products in all cities, which will minimize the distance he has to travel to deliver all the things in all cities. So we have to construct a Hamiltonian circuit basically here in this graph, which uses all the vertices exactly once and edges also, so that the cost will be minimized. So he can use this path from A to B, from A to B, B to C, C to D, D to A. So this is A, B, C, D, A. This is one example of Hamiltonian circuit. He can use A, C, then B, then D, and then A he can use this path also. A, C, then B, he goes to B, then to D, and then to A. This is in first case he uses from A to B, B to C, C to D, and D to A. So A to B, B to C, C to D, and D to A. In the second case he uses A to C, C to B, B to D, and D to A. A to C, C to B, B to D, and D to A. So he uses all the vertices exactly once, and the edges also. So this is a Hamiltonian circuit. This is also a Hamiltonian circuit. There are other possibilities also. He can go from A to D, D to B, B to C, C to A. From A to D, D to B, B to C, and then C to A. So another Hamiltonian circuit could be A, D, B, C, A. There are some other possibilities also. You can try yourself. Now we have to investigate what route he uses so that his distance is minimized. Now if he chooses the first route, for example A, B, C, D, A, from A to B he has to travel 30, from B to C he has to travel 30, from C to D 25, from D to A 40. You can see this here, from A to B 30 kilometer, from B to C 30 kilometer, from D to C to D 25, and from D to A 40 kilometers. If we sum up all these distances, we get 125 kilometers he has to travel. If he chooses this route A, B, D, C, A, the distance travel will be 30, 35 plus 35 plus 25 plus 50 is equal to 140. All other routes will give him these distances in kilometer. So what is the minimum distance? Obviously 125 and 125 here. So either of these two routes he can choose to deliver the products in 4 different cities, so that he has to travel the minimum distance in kilometers. So either he can use this route or this route. So thus either route this or this gives a minimum total distance of 125 kilometers. कितना रह गया टाइम? हो गया? हो गया टाइम कितना हुआ?
36.
पहले कितना था? 38. काफी है?
और लेक्चर कितना है?
हो गया बस. फिनिश कर दूं? मैं फिनिश करता हूँ वहाँ पे आप.
हाँ लेक्चर कंप्लीट.
अब एंडिंग स्लाइड में दे देता हूँ, बाकी ये मैं नेक्स्ट लेक्चर में ऐड कर दूंगा. ये दोनों इकट्ठे लेक्चर्स मैंने बनाए हुए. फॉर टुडे इट्स इनफ आई थिंक. वी स्टॉप here. And what we have discussed today, we have discussed Euler circuit and how to construct or how to find an Euler circuit in a given graph. Euler trials, how to find an Euler trial. We have discussed some examples, and we have found an Euler trial. We have also discussed Hamiltonian circuits and a travel salesman problem, which is a very famous problem. Today we don't have much time to discuss matrices and graph. Inshallah we shall discuss matrices and graphs in the next lecture, and some other topics relating to graphs. So until the next lecture, Allah Hafiz.